Okay, I assume you can hear me. Oh, I see that live stream starts here. Okay. Very good. Just bear with us a little bit. Is the sound okay back there? Can you hear me? Okay. I'm not going to increase the microphone volume here. Okay, perfect. Okay. So welcome everybody for today's computer architecture lecture on memory latency. This is the lecture 9. And with this, hopefully we will be done with the focus on DRAM memory. And in the like tomorrow, you will see some more of the exciting emerging applications. And I guess we will continue with SSD after that, roughly. But of course, we cannot get rid of memory, right? So it's like today we will talk about that. It's always a fundamental piece of the computer system that has a lot of bottlenecks in it, and there are a lot of problems to solve here. So, so these are the 4 key current directions that our group and pretty much the whole field actually focuses on. So we already talked about this security, reliability, safety issues in the last 2 weeks. And I guess you're already familiar with the energy efficient architectures and memory-centric computing from the first lectures. And today we will talk about this low latency and predictable architectures. And then later on, you will see a lot of focus on AI, ML, and genomics applications and some implications on medicine and health. So basically, outside of the computer architecture scope, what we want to do is to solve the hardest problems in the world, right? So global warming can be one of them, for example, or like there are these kind of problems in everyday life, right? So we want to solve these kind of problems. And if you actually formulate these problems seem quite similar to the problems you're dealing with in the computer systems. Or some of the hardest problems are just like applications of what we can do in computer architecture, right? So this is, for example, to find out the or sequence the DNA of living organisms, right? So you need really high performance and scalable and low energy or low power computing devices to perform all these. Yeah. And another fascinating field nowadays is to understand how brain works, build machines that work like brain, also make machines talk with brain, right? And all of these are coming with like some fundamental challenges in computer architecture, and they are like quite relevant to the latency problem that we will talk about today. So okay, do you guys know about Maslow? Okay, I guess Juan already went through this. So, you know, in this pyramid, we have very basic needs in the bottom. And then not lower priority, but it's like more advanced needs, let's say, in the top as you go, as you climb in this pyramid, right? So we need to have energy. We need to start with the energy, right? Without energy, nothing is possible. And without reliability and security, you can also consider that as like reliably having energy as well, right? It's like it's hard to exist pretty much, but it doesn't stop there. Of course, we need to have we need to climb up in this hierarchy, and we need to achieve better things so that we can actually make sure that our reliability, security, energy, everything is intact. And yeah, so the low latency, or in another word, reacting to some action is really important, and it actually improves the speed in every layer of this hierarchy. So yeah, I was gonna give a current example, but I hesitate now. I'm just gonna move on. So basically, if we focus on the computer architecture, it's really important to have low latency. So I'm not sure what you think of when I say low latency or latency. So I'd like to ask a question about. So what do you think like? So we have a concept called throughput, for example, that I guess you have become familiar during those PIM lectures. So what do you understand from latency? Do you is it clear like what is the difference in between? I see someone nodding. Okay. If you guys want to speak up, feel free. Or I can just move on as well. So so to motivate latency more, we can talk about some different domains. This is one of them. So you know, as we have more smart devices in our lives, we have more competition in the edge devices, and this is because we're trying to achieve low latency and high bandwidth without the need of like not need of, but without bottlenecked by the general internet uncertainty, right? Or like long latencies in the internet. So we want to achieve these high performance computing, low latency, high bandwidth, everything in the edge devices. So this is a talk that is around like 3 years old from Sister. It's from Satya, Mahadev Satya. Yeah, so this is in this talk, Satya talks about the current challenges of the edge computing devices and emphasizes the importance of latency. So I'd like to encourage you to look at that, because so if you look at like what edge computing does for you, it's like a lot of analytics, a lot of services. You also have some security implementations over there, and there's like there are many applications basically that you really need them to finish in a very small amount of time, so with very low latency. Okay, so he gives an example actually in this talk that this is so this is the latency of human cognition from some resources. Don't cite me for those numbers. So if you look at like how fast human brain can do something, face detection is around like 700 millisecond, recognition is around like 370 to 620, right? So like hearing a sound and understanding if it's coming from a human, it's like 4 milliseconds. So can we achieve these? Like, can we beat these latencies in our computing devices for these tasks, so that we can have some superhuman or like something better than what humans do today? Okay, so yeah, I highly recommend you to go watch Satya's talk. It's quite inspiring. So another thing here is the have you guys seen this device before? Maybe in part of this lecture or digital design and computer architecture. So this is something called Minion. So basically you put a sample inside this device, and this device generates reads the DNA sequence out of it. And this is a really like handheld small device, and they use this for doing the genome sequencing in the field. And this is important for detecting outbreaks, for example, right? Or detecting some existence of a virus or things like that. And these can have really like immediate implications or impact in the human lives, right? And this is really important. And you don't want to basically drop this sample here and wait this device to run for 15 days and get the result for you, because 15 days can be too long for virus to take over your body, right? So this is a latency critical application that I can give some example of, and you will learn tomorrow about these more detailed. But it's just an example for now for motivating low latency. Okay. So yeah, so Professor Mutlu talks about this dream that is really fascinating, actually, to have an embedded device that can perform comprehensive genome analysis in real time within a minute. And there are a lot of challenges to achieve this. But yeah, so there are like some energy efficiency, performance, and security challenges, of course. But everything is bottlenecked by the memory when you look at the current applications. And we really want to have memory really in high speed, and we want to access data or update data at a very low latency. And there are cases that you can increase your bandwidth. We will see about them, but you cannot improve latency, or if you do not improve latency, you're actually bottlenecked by the latency. Improving bandwidth does not make any benefit to you. So, okay, so this is a general properties of data-centric architectures. So we want to do the processing where the data resides, because we want to be like energy efficient and high performance, right? So you don't need to move data, you can move the computation. Okay, that makes sense. We already talked about this in the first weeks. And today we will talk about this low latency, low energy data access. And you will also get some lectures about how the data storage can be low cost, and how can we do processing in data storage, and how we can intelligently manage data. Okay, so there are some fundamental trade-offs in latency. So if you look at current memory technologies, so this is a plot from 1999 to 2017. It's a little bit outdated. I will show a more up-to-date one later on. But this is showing the picture quite straightforward. So if you look at the capacity of the DRAM or memory chips, you observe that there are like 2 orders of magnitude increase in 18 years, right? To 128x. This is like crazy. And you can get this with like technology node scaling, also improving your design, making it density optimized and things like that. And this is what the industry is shooting for. So this is their first order target. And when we look at bandwidth between the memory and the processing elements, basically you have like more than an order of magnitude increase here, 20x in these 18 years. But if you look at latency, it's really pessimistic, right? Latency did not improve much compared to these two. And it is really a problem today, because there are a lot of applications. I gave an example of some of them, but there are more applications that are actually limited or bounded by the memory access latency. And sometimes you cannot get rid of that, no matter like how much you change your application or improve your algorithms. So memory latency remains almost constant, and it's a problem. So this is a closer look. So over there, it was just showing the improvement, right? So here we look at the actual latency numbers. And for some fundamental memory operations like activation, recharge, precharge, and charge restoration. And over years again, you can see that it's pretty much constant. So it decreased at some point, and it increased again here, for example, for precharge and activation. For restoration, it follows a decreasing trend in the recent years, but it's not really like improving as much, right? And this is a more up-to-date plot from an ongoing work. So you can see so this is again the latency in nanoseconds, and here you see the capacity, chip capacity in kilobits, right? So note that, you know, this right side of the curve is logarithmic, left side is not logarithmic, or like, yeah, semi-logarithmic by the power of 2. This is power of 10. So so this magnitude of the difference in the curves are not the same for the black curve and the other curve. So if you look at TRCD, it's reduced from around like 64 down to like 16 between 1970 and 1975, right? Or like these periods basically until like 1980s. And then it followed a constant, almost constant trend. Cache latency means like column access latency. If you remember, when we want to access data in a DRAM row, we open the row and then fetch the content to row buffer, and then we perform some column accesses to the row buffer, right? So this is the latency of those column accesses. And it also follows an increasing trend, but it's almost like, yeah, pretty much saturated here. Actually, that's the same for TRAS and TRC as well. So these are also like some fundamental latencies in the main memory, and they also seem to saturate while we try to improve capacity more and more. Okay. So DRAM, I said that DRAM latency is critical for performance. There are a lot of works in the field showing this, that, you know, it's important for in-memory databases, graph tree processing, this in-memory data analytics applications, and data center workloads. So long memory latency causes for performance bottleneck for all these workloads, and we need to improve memory latency. I hope this is enough motivation for like explaining why latency is important. Do we have any questions up to this point? Yeah, sure, go ahead. Could you try using the microphone? Let's try it again.
Does latency depend on the capacity? So if we're looking at the same capacity DRAMs, does the latency improve more than what we've seen here?
I do not have data on that. I highly doubt it though, because when you look across years in this kind of time scale, you don't have the same capacity going. So like newer chips are always trying to increase the capacity. So it's highly like unlikely that you can find a few kilobit capacity chips today, you know? Yeah. So in my experience, there is not much difference actually. They pretty much have the same parameters when you look at the data sheets. But of course, to make some conclusive, you know, statement here, I need to look at the data in a more rigorous way. Any other questions? I'm trying to see if there's anything on YouTube. No, okay. So I'll talk about this work that was published in 2019 by Sogata Ghosh. He's a professor now in University of Illinois Urbana-Champaign. We had the pleasure of collaborating quite a bit in the past. So this is a product of one of those collaborations. Here, what they look at is like when they analyze the workload access behavior and how this access behavior is affected from different DRAM standards and different constraints that they impose, and shows that actually like new DRAM types can even increase latency. So I guess it will be clear in a little while. So you know, manufacturers are developing many new types of DRAM, and it limits the performance and energy improvements, and new types may overcome some limitations. This is the hope. But yeah, memory systems now serve a very diverse set of applications and can no longer take a one-size-fits-all approach. So I will keep using this word repeatedly in this lecture. It's important. One-size-fits-all approach does not seem to work for latency works. or in the modern systems for that are sensitive to DRAM latency. So the question this paper asks is like, which type of DRAM I should use for which application? And they test like a wide range of workloads on wide range of DRAM standards, and they come up with a lot of observations. I highly recommend you to go and check those, at least watch the lecture. And I will show a few of them here. So this is a comparison table that, I mean, you don't have to know every detail here, but this is just to show some trends. Basically, in DDR3, we didn't have banks. Sorry, we had like 8 banks per rank. We didn't have any bank groups. When we moved from DDR3 to DDR4 in 2010s, manufacturers and the consortium JEDEC decided to have more banks in a rank. It's like the number of banks is doubled to 16. And they also introduced bank groups, because to deal with all these banks, you need a additional step in the hierarchy. So in a DRAM rank, you have 4 bank groups today in DDR4, and each bank group has 4 banks. So do you like, I don't know, does it ring any bell that, you know, oh, there can be like this kind of shortcomings or not? Maybe. Doesn't have to be actually like quite clear at this moment. So the reason that we increase the number of banks is that it gives us parallelism. So you can access these banks not completely independently, but you can parallelize a lot of process here. You can hide some of the latencies, and it gives you more bandwidth. But when we have bank groups, for example, here in DDR4, now there's another level of hierarchy. There are more multiplexers on the critical path, and you observe that the latency actually increases to access a piece of data. And this is not really good. And you see, like, when we look at different types of memories, HBM, HMC, which is not continued anymore, GDDR5, wide IO, LPDDR3, or LP series in general. So there are like many different design decisions taking place here. When you look at the internal DRAM array, it's pretty much the same. There's not much difference actually, but they keep changing how they organize how they organize these DRAM arrays within the DRAM chip, right? So they change the geometry. Like some of them go for like 3D, some of them are ScaleNet 2D, and some of them have bank groups. Some of them are optimized for low power, but there is not much focus on latency. And as I showed earlier, in some newer standards, you can observe that the latency actually increased. And here is the implications on the real workloads. So we have some workloads on the x-axis here, and you have the speed up on the y-axis. So 1.0 means like you have the same performance as you would have using DDR3 memories. And if you check like some of these curves, for example, this red curve, which is HMC, or this green curve, HBM, or this blue curve, DDR4, in parts, actually, for some workloads, they go below 1.0, right? So this means that you update your memory standard from DDR3 to DDR4, or HBM, or HMC, and you end up losing performance. So this is quite weird, right? And the reason is they have they are like latency sensitive workloads, and they do not benefit from more parallelism that these standards provide. So it's just not a good fit. So yeah, the takeaways from this this paper are like, DRAM latency remains as a critical bottleneck for many applications. Bank parallelism is not fully utilized by a wide variety of our applications. And special locality continues to provide significant performance benefits if it is exploited by the memory subsystem. And for some classes of applications, low power memory can provide energy savings without sacrificing significant performance. But in general, you can say that latency is quite a problem still. Okay. I guess you can go check this paper, and you can also find the open source tools in the GitHub page of this paper, and you can find the full paper on archive on Professor Mutlu's website. And these are the all set of references for this work. Okay, let's go back to memory latency problem. So this is a limiter of system performance and energy efficiency. And it's becoming increasingly a bigger limitation because of higher memory contention in multi-core and heterogeneous architectures. So it exacerbates the need for bandwidth and quality of service problems. And it increases processor design complexity due to the mechanisms incorporated to tolerate memory latency. So in computer architecture, there are like many ways of addressing these performance issues. One of them is caching. So are you guys familiar with all of these? So with caching, you move the data to a closer location, in a location that you can access in a faster way, right? So, I mean, practically, you actually reduce the latency, but not fundamentally. It doesn't reduce the latency of the hardware itself, but you can hide some of that latency by bringing it closer. You can prefetch data to a closer location. You can enable multi-threading, so you can hide overlap latencies. You can make use of out-of-order execution. So it tolerates some of the latency penalties, but not completely gets rid of them. So these are like some general approaches when we look at the literature. And if you look at the dates, 1965, 67, 64, 67, these are like quite established old approaches, right? But the thing is, none of these fundamentally reduce memory latency. Fundamental reducing memory latency means like within the DRAM chip, we need to reduce the time that we spend to access data. Okay, so there's another example. This paper is called Runahead execution. It's something larger than a paper actually. It's more like a fundamental idea. This is Professor Mutlu's PhD dissertation, actually. Like in his PhD years, he was working on this a lot. So I will just explain what it does. So if you have perfect caches in your system, you do computation, and then you do some like additions, multiplications, other arithmetic operations, logic operations, right? And at some point, you need to load the data, a piece of data. So you need to go to memory, fetch some data. And if your caches are perfect, this load causes a hit in the first level of cache. And then in the next clock cycle, you can still keep computing, right? Because it doesn't delay anything. You don't have to wait for the memory request. And the second load comes, and then it also hits, and then you continue computing. But this is a very optimistic scenario, right? This doesn't happen. So if you have a small out-of-order instruction window, what happens is you do computation, a load comes, and then you observe, you go check the first level cache, it misses, and then there's a large stall here. And this stall comes from accessing the higher level of cache. If it also misses higher than that, if it also misses, you need to access main memory. If it also misses, you need to access SSD, or I don't know, maybe you're streaming something from YouTube, you need to access YouTube servers, right? You need to, you need to wait a lot. And then once the data is in the processor, you can continue computing, and then another load comes. And then another miss happens, another stall happens. So this is not really a good case, right? So what Runahead proposes is that, okay, we are doing computing and the first load misses. So we have to wait a little bit. But let's switch to a mode called Runahead mode. So in this mode, what we do, we just like speculatively keep doing the computation. And at this point, we will see another load. And maybe it will also miss, but that's okay. We can just start executing this load, right? Without waiting for the first load. And then it will also miss. It will also create a lot of stall. But especially in this part, you can see that the latency of the first load and the latency of the second load are largely overlapped here. And then you will have the data for load 1 here. And then you will keep doing computation in normal mode because load 1 already returned. Now you have like one outstanding load, load 2. And then it will also return at some point and you will continue computation. And as a result, you save all these cycles. You improve your application performance. And yeah, congratulations. So actually, after Runahead execution papers publication, some companies, especially the Sun, analyze it. So there's a talk from 2008 that shows this data. So when you have the sculpting, basically the same principle, right? For a given cache size, you get about 40% better performance. So let's say you're okay with, you have some performance targets. You will be okay with some performance. Let's say this much performance is good. With this execution model, you can actually achieve this performance at around like 1 megabyte cache, while you would need around like 8 megabyte cache. So it buys you some 7 megabyte cache, right? So this largely reduces the area you need in the chip. So now you can do more things with this area. Maybe you can put some accelerators. Maybe you still put a large cache and get even more performance, right? Or you can just reduce your chip size. That's also possible. So this is a full reference to Runahead execution. I'd like to highlight that it was picked as like top picks in 2003. So basically, this IEEE micro top picks thing is they look at all the papers that are published in the top menus in that year, and they pick the most influential or most promising ones, and they ask you to publish something shorter to recover all that idea so that there will be more visibility. And then this, okay. Yeah, this is another page of reference here. Okay. And there are some readings. So there are a lot of follow-up works of this Runahead execution, efficient Runahead execution, address value delta prediction, and wrong path events. So these are like very good reads. They are recommended, but you should read this paper. I assume we will have this as part of homework as well. Yeah. And you can also watch this lecture. You have the full link here from Professor Mutlu. So when, yeah, so when, wait. Yeah, I think that's it. Yeah, you can watch that. Okay, yeah, this is the other one. I was looking for this reference. So this paper in 2021, years after it was published, awarded with the Test of Time Award. So this award basically recognizes the works that have a high impact over a large amount of time. And it was selected to be awarded with this award. And Professor Mutlu gave a talk in HPCA 2021, a retrospective talk about Runahead execution. So please take a look at that as well. Okay, so these are again, conventional latency tolerance techniques, and they do not fundamentally reduce memory latency. I think you can say that Runahead execution is also one of them. It's a great work. and it improves performance a lot, but latency problem is fundamentally still there. So we need to tackle that. And the reason is modern DRAM is not designed for low latency. Main focus is on cost per bit. You want to improve the capacity. You want to put more capacity into your DRAM chip for each Swiss franc you paid for it. Okay, so modern DRAM latency is determined by worst case conditions and worst case devices. So I talked about that term one size fits all. So it is actually used. They account for the worst case for everything, but it is not really necessary, and it requires much of memory latency. Yeah, it requires more memory latency for the common case unnecessarily, and our goal is to reduce the memory latency at the source of the problem. Okay. So what causes the long memory latency? So reason one is design of DRAM microarchitecture, because it is designed with the goal of maximizing the capacity per area and not minimize the latency. And it also follows this one size fits all approach. I will show this slide several times, but I'd like to go over it once at least. So you use the same latency parameters for a given DRAM chip for across many temperature levels, across many chips from the same product family, across all parts of a DRAM chip, whatever your supply voltage level is, within the range, of course, and independent from your application data. Okay, so let's look at the inside the DRAM chip. So this is a DRAM module, and this one of these black rectangles is your DRAM chip, and this is a DRAM chip's picture here, right? So in the design, there are a lot of things, a lot of goals: cost, density, reliability, bandwidth, parallelism, power, energy. But latency comes like much later in the list. So this part is a DRAM bank, and you have the bank I/O here, and you have the cell array and some local sense amplifiers that help you to sense the voltage levels in these cells. And there are row decoders here. And when we look at the sense amplifier, inside the sense amplifier, what we have is just a back-to-back inverter. This is very similar to SRAM cell as well, actually. So basically, assume that you have high voltage here. This inverter will force to have low voltage here, right? And this low voltage will force this inverter to make this line high voltage again. So it's a quite stable circuit here. You can, as long as you have power, you can store your data here, right? And you have some enable signal here that enables the inverters so that you start this sensing and amplification process. So yeah, if you have like VDD here and ground here, it means a logical value. Let's say in this case it's logical 1. And if it's the opposite, 0 here, VDD here, then it means logical 0. So this is a symmetrical structure, and it's like out of the whole circuit design, it doesn't mean really anything which one is which, right? But like one is one, the other one is the other one. Okay. So you basically have some bitline voltage when you access DRAM cells, and you have a threshold voltage. So these are like on the opposite sides of the sense amplifier. And once you enable these inverters, if this threshold voltage, if VT is larger than VB, basically, the site that VT is boosted to VDD. So you can think of this as like a pull-up circuit or pull-down circuit as well, because inside the inverters we have pull-up and pull-down transistors, if you remember. And yeah, so depending on like which site is slightly larger than the other one, you boost the lower voltage to ground and higher voltage to VDD. And let's go back to DRAM cell. DRAM cell basically stores the bit of data in a capacitor as a charge, right? So in the empty state, we don't have charge, basically. It can be logical 0. You can also identify it as logical 1. The important thing is to have like different states for these two. If it's fully charged, it's the other, right? So if this is 0, this is 1. If this is 1, this is 0. So the thing is, this capacitor is quite small because we want to put many of them into a very small chip area. So it contains a little bit of a charge and it cannot drive circuits. And when you try to read it, actually, you use the charge inside this capacitor to drive some lines. So it's destructive, right? So reading destroys the state. Okay. So what we do, we connect these capacitors to sense amplifiers via bit lines. So basically, this is what happens. So there is a transistor here that controls if this wire is being connected to this wire or not. And in the initial state, you have half VDD in this bit line. Once you connect this line, so this capacitor has like full charge. So it loses some of its charge, and it creates some deviation in the bit line voltage here. And it's only a delta, like it's a small deviation because the capacitance or impedance of this capacitor is significantly smaller than what you have in the bit line. So this is slightly higher than half VDD, but this part is half VDD. So you enable the inverters, and this part is boosted to VDD, and this part is boosted to ground. Okay? So once you boost this bit line to VDD, then it goes back and restores the charge in the cell. So you at the end of this whole process, you again have the full charge in the capacitor. So when you read, it was destroyed, and then you put it back. Okay, this is a building block for a DRAM chip, and you put many of these cells, and in like different in like horizontal and vertical lines, basically, and it becomes a two-dimensional cell array, right? And in between, we have many of these sense amplifier circuitry. And you have a row decoder here on the left, based on so you provide a row address to this row decoder, and it enables one of these lines that turn on these transistors, and then those cells are connected to the sense amplifier, and you read the data in that way. So this is a more detailed background of what we talked all in the past few lectures about DRAM background. So you have this array of sense amplifiers that is like typically as large as 8 kilobits, and then you have these cell arrays. And then you put many of them together, and they form a bank, basically. And then they share a I/O circuitry here called bank I/O, and then you read a 64 bits of data every time. So you provide the row address to these row decoders, and column address to bank I/O, and then as a result, you get some data out of this DRAM chip, and it's like yeah, you get 8-bit in this case, and you have many of these banks here inside this chip, right? And they all share an internal bus, so you cannot simultaneously access these structures. They still share some circuitry here. They need to time share that circuitry for sure. But internally, you can overlap some of their latencies. Okay, so you activated a row. Let's say you provided the row address here, and this row is activated. You move this data to this local sense amplifier here. And then when you want to read-write the column, you send the column address to this bank I/O, and then bank I/O gets this data. And then at the end, basically, because you cannot keep the same row open all the time, you want to access the other rows as well, you need to precharge the bank. And it just like disables these sense amplifiers and disconnects that row. And as a result, you like open and close the row. Okay, so all these things are explained in detail in this DRAM bulk bitwise execution engine. I think you're familiar with this paper because this is the foundation of Ambit, right? So is this this is the book chapter. Okay, yeah. I think from the first lectures you're familiar with this. Okay, okay, let's go back to our story. Oh, okay. I need to master the what? Runahead is how you compute the addresses that you need to load in the future. I guess that's central to the problem, but maybe you can. Yeah, so in this talk, it's not really like in the focus of the talk, so I don't want to get into details about Runahead execution. But basically what you have over there is that you have the upcoming instructions, and you can speculate which instruction will be issued, right? And you basically go ahead and I mean, you can have like which loads instructions are coming in the future, and you can start executing them earlier. So that's the like main high level key idea. And yeah, of course there are many details here that you need to tackle with, and there are a lot of challenges. And for those, I just want to refer you to that Runahead lecture that I showed. Yeah, so Mohammed, the head TA or instructor of this course, is telling me that we will have a profession lecture. So you will have more details about this whole idea in those lectures. Just like stay tuned for the upcoming weeks. Okay. Okay, so another thing we will walk through is I cannot say it. I'm sorry, tiered latency DRAM. So this is another paper that is quite impactful actually, and the idea is quite simple, but I'd like to walk through the idea with you. So basically here we have DRAM chip, we have some global IO circuitry and the cell array on the top, and the cell array has the subarrays, and between each subarray we have the sense amplifiers, right? And okay. So this DRAM latency, if you want to calculate the DRAM latency, it's basically the latency of the subarray plus the latency of the IO. And what causes the long latency is the latency in the subarray. It's the dominant one because IO is working quite fast compared to the analog operation and the sense amplifier. So so what the main observation here is that in a subarray, let's say you have 512 cells on a column, meaning like 512 rows, and you have sense amplifiers here. So if you have a larger sense amplifier, you can sense this faster. If you have a longer bit line, it amortizes the sense amplifier cost, and it gives you small area because, so, okay, let me put it this way. So the sense amplifiers are significantly larger than the cell size. So whenever you put sense amplifier, you sacrifice some capacity, right? And to amortize for that capacity loss, you connect like many of these DRAM cells into a sense amplifier, and by doing that, you can get small area, high capacity. And as you get like larger bit lines here, you have larger capacitance, and it causes larger latency and power. So this is the main trade-off here. If you make your bit line shorter, you sacrifice capacity. If you make it longer, you sacrifice latency. So if you have long bit line or short bit, so short bit line is faster than long bit line. Long bit line is smaller than short bit line. And the trade-off is between area and latency. And when we look at the normalized DRAM area with latency, we see this kind of curve, right? So as we go low, As we go lower, it's cheaper. As we go to the left, it becomes faster. And the commodity DRAM commodity DRAM implements something in this trade-off, right? So it's usually like 512 cells. Today, it's actually even in some subarrays, it's significantly larger than this number. I observed some subarrays around like 800 rows large or 1,000 rows large. So the bit lines are getting longer and longer actually. So you have larger latencies as well. But depending on how many cells are connected to a sense amplifier, you can actually achieve lower latency or, higher density. So our goal is here, but we don't have any design point here, right? We can only travel on this curve. Okay. So long bit line means small area and high latency. Short bit line means low latency and large area. And what would you do to find the middle point? Any idea? Yeah? You can mix it. Yes? That's a very straightforward way. Yes, that's really good. So what we do is something similar to that. So we get small area from the first design and low latency from the second design. But so we split this subarray into these two chunks. But we need some isolation here so that we can have short bit line here and long bit line here. So what we do is we put some isolation transistors in between. And this is our design basically. So you have small area using long bit line, and you have low latency for a subset of the rows, right? You cannot have like the best of each world for all of the rows. So you introduce some heterogeneity here. If you want low latency, you have those rows that have low latency. And in general, your chip is not very large. Okay, so this is commodity DRAM. It has around like 52.5 nanoseconds of latency. And so this TRC is the latency between two activations, basically. It's just like, you can consider it as like a minimum latency that you need to spend for accessing a row. And here is another plot about DRAM power. So in TlddRAM, we have the near and far regions of subarray. And in the near region, we have much lower latency and a little bit larger latency in the far region. And when we look at the power, for the near region, we reduce the power consumption a lot and increase the power consumption in the far region. So now there's another trade-off, like where you want to put your data, right? And this, in general, increases the memory overhead around like 3%, mainly due to the isolation transistors. And this was our goal. Near segment happens to be in this region, which is much better than any point in this curve, actually, based on this goal definition. And the far segment becomes here. So it's a little bit worse. But having near segment, if you can exploit this, things can work well. So TlddRAM is basically a substrate that can be leveraged by the hardware and our software. It has many potential uses. It uses near segment as hardware managed inclusive cache to far segment. It can also use near segment as hardware managed exclusive cache for far segment. And you can use this based on some profiles by the operating system. And you can simply replace DRAM with TlddRAM, and it will allow you to do like whatever you want to do, basically. It's another like dimension in your design space, right? You can do many things. So going back to high level, in a DRAM array, we have sense amplifiers here, near segment and far segment. So you can consider far segment as the main memory and near segment as the cache, because it has much lower access latency. And our challenge is how to efficiently migrate a row between segments. So now I want to put a row here so that I expect to access that row frequently, and I want to access that row with low latency. So I want to put it in the cache. How can I do that? And how to efficiently manage the cache? So let's look at the first challenge here. So we want to basically, so this is our near segment, this is our far segment, and this is our source row, and this is the destination. So I want to take the data from this source row, put it into the destination, so that next time I access this row, I will access it with a very low latency. So a naive way of doing that is reading the data from the source row to memory controller, and then writing it back to this destination row. So it requires a very large latency, unfortunately, if you remember from the processing memory lectures. And it induces very high latency, right? So how would you solve this problem? How would you move data from the source to destination without going through the memory controller, which is incurring a lot of high latency? Any ideas? Row clone? Yes? Exactly. So they share bit lines. You transfer data in parallel across these bit lines. You activate the source row. You you fetch the data to sense amplifiers and activate the destination row. And the sense amplifiers are already biased and already amplified the signal. It will be just restored into the second row. And the migration is overlapped with the source row access. It just requires additional 4 nanosecond over row access latency, but that's all. So how can you manage this cache efficiently? So I guess we will not go through that. So on the x-axis here, we have like increase in number of cores, and we look at the normalized performance. We see that TlddRAM provides us with some significant performance improvement around 12, 11, 10%. And it reduces the power consumption accordingly. So in general, we also get some energy out of it, right? So it's like around like 24, 25% power reduction. And using near segment as a cache improves performance and reduces the power consumption. Okay? So if you increase the number of rows in this near segment, you have different trade-offs, of course. And your performance improvement increases here with larger cache capacity, and then it starts decreasing here. Because as you increase the number of rows in the near segment, you end up having higher latency because now there are more rows. The near segment's bit line is longer, so the access latency is larger. That's why you see the performance slow down after some sweet spot here. Of course, this is for like one manufacturing set of manufacturing parameters or design parameters. So for different technologies, you can have this this sweet spot in different places. So this is the maximum IPC improvement you can get, and it's with like 32 rows in this evaluation. And by adjusting the near segment length, we can trade off the cache capacity for cache latency. And this is the tier latency. Okay. So I think it's a good time to stop. I'm going a little bit slower than what I was shooting for, but I think we are getting tired a little bit as well. So I will not go through Lisa. Let's do a break for, let's say, 7 minutes and come back at 2:20. Is that okay? Thank you. Okay. Now it works, right? Okay. Oh yeah, then I need to repeat. I'm sorry, in the previous part, the camera was frozen for some time. We realized that and we believe that we fixed it now. And I forgot to turn on my camera, sorry, microphone as well. So that's also fixed now. Okay, let's start with Lisa. Lisa is published in HPC 2016, and it's called low cost. The long name is low cost interlinked subarrays. It's a neat idea, I believe. So the motivation is that bulk data movement is a key operation in many applications. As we see in TlddRAM, we need to move rows around within the DRAM chip, and it has great benefits, right? So memmove, memcopy are also some examples that that consume 5% of cycles in Google's data center. Okay. Basically, we have CPU and memory. We need to move the source to a core and then move it back to destination. So if you don't have in DRAM data movement, right? And this is a very long latency, and it requires a high energy consumption because of the off-chip data movement. And it also creates a lot of stall cycles for your applications, and it increases the execution time as well. So your idle power consumption also contributes, and you end up having even higher energy consumption. So the idea is to move data inside DRAM chip. So within a bank, we have these DRAM cells, and they are organized into different multiple subarrays. And yeah, let's say you have like 512 rows in each subarray, and the row width is like 8 kilobits. And you have an internal data bus of 64 bits. So the low connectivity in DRAM is the fundamental bottleneck for this bulk data movement. And our goal is to provide a new substrate that allows this this vast parallelism actually across different columns in subarrays. Okay. So the proposal is low-cost interlinked subarray. It's a fast bulk data movement between subarrays, and it uses a wide data path via isolation transistors. So you guys are familiar with row clone, and if you remember in row clone, you can activate a row, put the row's information onto bit lines and the sense amplifiers, and then you activate another row, and you have the copy of the first row in the second row as well, right? This is how row clone works. But it only works if these rows share bit lines and sense amplifiers. If they do not, if your source and destination are in different subarrays, what Lisa does is to put these transistors across subarrays so that you have a versatile substrate basically that connects these subarrays, and it allows new applications such as fast bulk data copy and provides significant speed ups, as you see here. Okay, so it also provides you with the option of in-DRAM caching. So if you have some, excuse me, if you have some low latency regions in your memory, and if you have some hot data, you want to move this to inside the that cache area, you can do that very fast. And you can also do the precharge very fast. This is a, let's say, added impact of this Lisa proposal that we will see in a little bit. So row buffer movement is a fundamental part of this. It moves a row of data in an activated row buffer to a precharged one. What it does is like, okay, so you activated a row in the subarray one. So you draw these bit lines with some voltage levels. Your sense amplifier is already in a stable position. Okay, so it's at VDD, and the bit lines bottom there are VDD over 2. So you basically connect these, you turn on these, right? And then a charge sharing starts between these two sets of bit lines. And you lose some voltage here. You basically increase the voltage of the second set of bit lines a little bit. And then once you activate the sense amplifiers, and that sense amplifiers are already active, So they collaborate to drive all these bit lines together. And as a result, you moved your data from the first subarray to second subarray. And yeah, so the range of this structure depends on the DRAM design. So you can make it across multiple subarrays. In this scenario, it can be like larger than 3 subarrays. How it works is that you have these 3 subarrays and you connect them all together. Sorry, let's not cut the animation. So you move data from subarray 1 to subarray 3 as well. So now you have more sources and more destinations. You can move data around really flexible way. And this model is verified with some SPICE simulations using the worst case cells. And they use some 45 nanometer library. And it seems like they can, yeah, okay. You can move like 4 kilobyte data in 8 nanoseconds. So this is like with 60% guard band also. So you have very large, basically, bandwidth here to move data around. And it only incurs like 0.8% DRAM chip area overhead. So this is a good example of what happens when you sacrifice a little bit of DRAM chip capacity and enable low latency, high bandwidth operations. So this is another piece of that paper, rapid inter-subarray copy. So the goal here is to efficiently copy a row across subarrays. And they use RBM to form a new command sequence, basically. So this is basically how you perform the operation that I just described. So you activate source row. It enables these sense amplifiers. And then you send this RBM command to connect these 2 subarrays. And then you activate the destination row. Once you connected these 2 subarrays and enabled these sense amplifiers in the bit line, you already have the data. And once you activate the destination row, it only gets in. So it's a very quick process. So it reduces row copy latency by 9.2x and DRAM energy by 48x, right? So this is really large benefits. Okay. This is another use case of this idea, let's say, variable latency DRAM. So you reduce the DRAM latency with low area overhead here, and you do this to, provide a better trade-off between the area and latency. So in long bit line architecture or short bit line architecture, the trade-offs. You have like more capacity or larger latency. So shorter bit lines allows you to access data faster. And you do that by like activating and precharging faster, right? So if we can reduce the latency of activation and precharge, then it would work well. And put in all these structures, like repeating them is inducing some high area overhead. So if you like make your subarrays really small for achieving low latency, then you will need to replicate these sense amplifiers a lot, right? So you don't want to do that. And what you do in this case, you reduce the access latency of hot data via heterogeneous DRAM design. So heterogeneity came back again. So this is the opposite of one size fits all. So Villa is the mechanism. It adds fast subarrays as a cache in each bank. So this is maybe closer to what you said, proposed earlier. So you have some slow subarrays and some fast subarrays. And the challenge is that you need to move data across these subarrays to cache it. And you need to do that frequently. And basically with Lisa, with these like inter-subarray connections, you can quickly move data from slow to fast subarray. And then you can just access fast subarray, and it will be your cache, and it reduces your access latency by like 2x and at only 1.6% area overhead. This is quite effective. Okay, so this is the other thing. This is how we reduce the latency of precharge operation. So the precharge time is limited by the strength of the precharge unit. So you have the precharge unit here inside the, okay, where's my mouse? Inside this, or like next to this sense amplifier, basically. Once you turn this on, it basically precharges the line over there. And if this structure here is strong enough, you can precharge your bit line really fast. If it is weak, you cannot perform that fast. And what we do here is to precharge the subarray using multiple precharge units. So instead of using a single precharge unit, now we have these connections across subarrays, right? So we use 2 precharge units for each bit line. And we drive them to the same voltage level from like both sides. So the whole precharge operation is much faster. It's yeah, the latency reduction is around like 2.6x in this case. Yeah, this is a quite nice read. I highly recommend this. This was one of the first papers that I read actually when I joined Subarray. I really enjoyed it, and I hope you will enjoy it as well. So this is the full reference. You can see some slides and source code here as well. So this is a relevant idea, CROW. CROW is so CROW stands for the copy row. It's another substrate that was published in ISCA in 2019. So here again, we tackle the access latency, refresh overhead, and exposure to vulnerabilities. By vulnerabilities, you can just replace that with RowHammer in this paper scope. So inside DRAM chip, we have these DRAM subarrays and sense amplifiers. I guess it's just the same thing over and over again, right? So this is the idea. So now we have these copy rows inside the subarray, and we have a dedicated decoder for those, and we have some regular rows. And what we do is we copy row from a normal row to sense amplifier, and then from sense amplifier back to one of these dedicated copy rows. And why we do that is to reduce latencies, as I said earlier. So how you reduce activation latency is that once you need to access this data, you need to activate this row, right? And it has some latency to bring this data to sense amplifier. And this is all about like your amount of charge in your cells and how much deviation you can create in the bit line, the length of your bit line, and all those things. So here, the key idea is that we have the copy of this data inside this row as well. So we can activate this row together with this row. So we will have more charge that we put on the bit line. So the voltage deviation will be larger. And it will allow our sense amplifiers to sense and amplify in a much faster way. So we use CROW as a cache where we reduce the access latency, just like using the mechanism that I explained. We also use it to refresh. So it reduces the DRAM refresh overhead, because now you can, when you can activate row faster, you can actually restore your charge faster as well. And it reduces the time you spend for a refresh operation. Okay. And I guess you can see that it's also a mechanism, it's already like by reducing refresh latency, actually it's already helping mitigation mechanisms against RowHammer. But it's on top of that also proposes a mechanism for protecting against RowHammer. I can explain it a little bit as well actually here. I'm not sure if it's coming in the following slides. I think it's not coming. So what you do for protecting against RowHammer is that, if you remember RowHammer, you keep activating rows and you cause some read disturbance in the nearby rows, right? So you keep activate this row, let's say, and then you create disturbance in these rows. So with CROW, you have a copy of that row here as well, right? Now, you can also serve some of your requests here. Or in this case, I guess like instead of serving here, instead of serving here, you serve it here. So instead of like this creating root disturbance on a weak row in this regular region, you create root disturbance on a strong row in some other region. So when you enable crow cache and crow ref, you can get 20% speed up and 22% reduction in the DRAM energy. And it only comes with the hardware overhead of 0.5% for DRAM chip area, 1.6% for capacity, and a very small buffer in memory controller. And this is the full references for Crow. And I believe there's a lecture as well. Yes, you can see the lecture video here. There's a short video, 3 minutes, another one, 16 minutes. And you can also find the source code for like all evaluation on GitHub. So I highly recommend to take a look at that. It's also a nice read. So clear DRAM is also another way of approaching this problem. So our whole trade-off is between DRAM capacity and DRAM latency, right? So clear DRAM is a very cute idea, I would say, that allows us to play with this trade-off, even in the runtime. So this is a paper published in ISCA 2020, and it's published by Hasan. He's a PhD student. He gave a lecture about RowPress the other week. I think he will give some other lectures as well, but I'll go through clear DRAM really quickly. So the motivation is that workloads and systems have varying memory capacity and latency demands. And in some cases, we might want higher capacity. In some other cases, we might want lower latency. And this is not a trade-off that we ideally want to make a decision about in the design time. So in the runtime, we want to also have some control on that. So systems miss opportunities to improve performance by adapting to changes in main memory capacity and latency demands. And our goal is to enable this in a way that it can be dynamically configured. And we basically define two modes of each DRAM row, a high storage capacity mode and a low latency mode. And we can dynamically switch between these two modes. It's a low-cost DRAM architecture, enabling this dynamic switching between max capacity and high-performance mode. And the key idea is to dynamically configure the connections between DRAM cells and the sense amplifiers, so that you can have a density-optimized so we already do that in a density-optimized open bitline architecture. You can have higher capacity or lower latency. What we do here is, so in open bitline architecture, what you have is, maybe I should show from here. So you have a sense amplifier on top and a sense amplifier in the bottom. So these cells are connected to the sense amplifier on the top. These cells are connected to the sense amplifier in the bottom. So this is a architecture that is used for optimizing for higher density. So from this design, we switch to this design. So we replace this connection with a transistor, and we add another transistor here. Also, we add this transistor here and replace this wire with a transistor here. So we have like some fine-grained control on which bit line will be connected to which sense amplifier, right? So when we're operating in max capacity mode, what we do is we just turn on the transistors in this way. So this just mimics the open bitline architecture, right? All the connections are identical to open bitline architecture. Because of these transistors, you might have some additional latency, but it's a low overhead. So you get the same storage capacity as the conventional open bitline architecture in this case. And in high performance mode or low latency mode, in other words, you basically turn on all these transistors. So when you turn on all these transistors, if you remember, within a sense amplifier, you have two back-to-back inverters, right? So two sides of the sense amplifier have to have the opposite data. So you store a data bit A here, and then in the next cell, you have the opposite of the A. So when you turn on this, you basically create voltage deviation on both sides of the sense amplifier. You increase voltage on one side, reduce voltage on other side, and from the sense amplifier's perspective, the voltage difference on two ends of the sense amplifier are greater, right? So it's much easier for sense amplifier to sense the difference and amplify it to the VDD and ground. So by doing this, you can actually reduce the access latency quite a lot. Okay, there's some terminology over there. We don't need to get into that because we will not dive into details. So basically, by doing so, you reduce latency and refresh overhead via coupled cell and sense amplifier operation. So as a result, you can reduce activation latency by 60%, restoration latency by 64%, precharge latency by 46%, and write recovery by 35%. So these are great latency reductions. And if you look at the impact of this latency reduction in the system level performance, you get like 18% speed up. You reduce energy consumption by 30% and refresh energy by 66%. Okay, so this is the full reference for TlddRAM. I hope Hasan will give a detailed lecture about that if we have time. Okay, I'll go through another paper, Subarray level parallelism. So this is to reduce the DRAM bank conflict impact. This is one of the older papers as well, relatively older. So the problem is that, do you have a question? Okay. Are there any questions, by the way? I don't see anything on YouTube. Okay. So we tackle the bank conflicts here because each bank conflict requires closing a row and opening a row. So it automatically adds the activation and precharge latencies into your access latency, and it requires your request to be serialized, and you end up wasting energy. So we do not want to do that. And our goal is to reduce the bank conflicts without adding more banks. How we do that? The key observation is that a DRAM bank is divided into subarrays, and each subarray has its own local row buffer. So intrinsically, within a bank, you have multiple subarrays, and you have some parallelism across these subarrays already. So this is your logical bank when you look at it high level, but in physics, it's actually implemented in this way. You have subarray, local row buffer, subarray. Okay. These are like all repeated backgrounds, right? And the second observation is that subarrays are mostly independent. So you have a global decoder here, global row buffer here, but within subarray, actually, you have the array and local sense amplifiers that are not affected from the operations in some other subarrays. So with these observations, the key idea is to minimally reduce the sharing of global structures, and you reduce the sharing of global decoder and global row buffer. Basically, what you do is like, instead of having a latch in the input of global decoder, you just replicate the latches to the output of the sense amplifiers. So once you put a latch over there, whatever you do in sense amplifier stays in the sense amplifier. It's like Vegas. So you activate a row that stays in the local row buffer of the sense amplifier, right? And you activate another row here, it also stays there. And nothing is, so these two sense amplifiers do not affect each other's reliability or operation in any means. And the global I/O is also not affected if you deal with these latches in a correct way. So you basically, it's all about like implementing this idea. You need to add some additional controls. I will not get into details, but when you need to read something, you need to read it from global row buffer, and it basically enables the latch on the whichever subarray your data is in, and then you basically have a shared interconnect here, basically, right? And you can just like switch on, switch off different subarrays. You can get your data accordingly. So the second read comes from here. Yeah. So this is the modification that you have. And the overhead is just like 0.15%. It's really cheap. And if you remember last week, I talked about hidden row activation. And we already observed that this kind of parallelism exists in some of the off-the-shelf chips today. So this paper was published, if I'm not mistaken, in 2012 or so. So after all these years, we see that some chips have this functionality. We can use it. We have a way of using it, but it's not something still officially supported. But if it's officially supported, it provides a wide variety of systems with different number of channels, banks, ranks, and subarrays. It can provide benefits to servers, streaming, random access, spec workloads, right? So it reduces the energy consumption by 19%. Hit rate improves the hit rate by 13%, and system performance increases around like 17%. And it only comes with the diary overhead of like 0.15%. So it's only a matter of DRAM manufacturers and JEDEC consortium to make this into the standard. And once they do that, and once they officially support this, memory controllers can get huge benefits of these. And I think this is, you can take this as like a preliminary evaluation, right? Once this is enabled, you can leverage this parallelism in many other ways today. Because this paper doesn't deal with RowHammer, for example. Now, today we have that problem as well. So for that solution, we need parallelism as well, as we saw in hidden row activation. So there are many more benefits that needs to be explored here, but we need some official support for those to make them in the real systems. Okay, so this is the full paper. And I'd like to refer to this paper from Samsung and Intel again. This is the same paper that I showed you the last week. They also talk about subarray level parallelism here. And they consider subarray level parallelism together with some relaxation on the write latency to DRAM. And they show that we can relax the write latency. And if we also leverage subarray level parallelism at the same time, we can actually provide great benefits. So it says 3% improvement on average. You might consider that like this is a low value, but you have to consider also that this paper is coming from Samsung and Intel, and their simulation infrastructure is closer to their products than many like infrastructure that is used in the academia today. So I guess we will have another lecture about simulations. You will see the trade-offs more over there. But yeah, when it comes to like industry papers, this kind of performance improvement is really important, considered important. Okay. So we went through a lot of things in the DRAM design. And we also will talk about the second reason, one-size-fits-all approach. I will go through some other papers. So it's already 10 minutes to 3, but we have a lot to cover. Maybe I'll not give a break here, but I'll wait for like 3:30, if that's fine for you. Okay. So, okay. So there's I'm not sure if it's completely safe to say that this is a mindset issue, but I think you can see some mindset issue here. So there is this approach of like having the latency is fixed and having this one size fits all kind of approach. So reliable operation latency is actually very heterogeneous when you look at inside the DRAM chip. And it also changes across temperatures, different chips, like parts of the chip, voltage levels, with a lot of things. And in high level, our idea here is to dynamically find out and use the lowest latency one can reliably access in a memory location. So there are multiple works that we studied for this heterogeneity from different aspects for different operations. The first work is from HPC 15, adaptive latency DRAM. Another one is flexible latency DRAM from Sigmatrix 2016. There's also a design induced variation aware DRAM published in 17, and Voltron in 17, and DRAM latency puff in 18, solar DRAM 18, true random number generators, and there are more actually. So we can basically leverage this heterogeneity, use these latencies in the minimum reliable points, and then we can provide better performance and improve system greatly. So yeah, we would like to find the sources of latency heterogeneity and exploit them to minimize the latency. Okay. So the manufacturing process is quite a heterogeneous process. So you get your chips out of wafer. Even within a wafer, depending on where your chip comes from, the chip's characteristics can be different. There are also imperfection in the machinery you use there. It's not, and also in the like silicon wafer, it's not like perfectly homogeneous, right? So there are a lot of variations playing a role there, and you can have some chip manufactured, and you can have like different parts of that design that show different latencies. And even like within the DRAM chip, you can have different features. So within a DRAM chip, you can have some slow cells, some fast cells, and you want to improve these leverage this heterogeneity to improve the latency, right? So why is our latency high? It's because DRAM latency is defined as like delay as specified by the DRAM standards, and it doesn't reflect the true DRAM device latency, and it accounts for imperfect manufacturing process in a conservative way, I would say. So you have all this manufacturing variation across different DRAM chips, and you have this kind of, let's say, latency distribution across DRAM cells. So what you see in the specification or in data sheets as the latency value is somewhere here. So your chip is much faster than what is written there actually. So this is like by definition, right? It says that if you use this kind of latency for this chip, you will have reliable operation. So the chip should finish that operation before that time passes, right? So in fact, you have much smaller latencies. And this is called like conservative timing margins. And DRAM time parameters are set to cover the worst case and also the worst case temperature. So for example, these latency values and some data retention values as well are defined based on like 85 degrees, operation at 85 degrees Celsius. But in common case, actually, you don't always operate at 85 degrees, right? So this is to enable a wide range of operating conditions. There's some good motivation into that as well, but it is actually showing the worst case. Also, they define these values based on the worst case devices so that they can improve yield. They can manufacture more chips in the assembly line, and basically DRAM cell with smallest charge across any acceptable device basically defines the latency and data retention kind of parameters. And this is to tolerate the process variation at acceptable yield, and this leads to large timing margins for the common case. Okay, so this work, another set of background, I'm just gonna move through that. So these are the operations that we will be focusing on: sensing, restoring the charge, and precharging the bit line, right? So, okay. I guess these are like quite clear what we are doing here, but maybe you didn't see this plot before. So, okay. So we look at the cell charge on the y-axis and time on the x-axis. So, and this is a cute animation here. So in the sense amplifier, we have half of the voltage, right? And in the cell, we have like fully charged. So we start sense amplifier at half voltage, cell at full voltage. And then when we enable the access transistor and the cell starts sharing its charge with the bit line, sense amplifier voltage increases a little bit while cell voltage reduces significantly. and it ends up somewhere nearby half VDD. And then since this value is larger than the half VDD, the reference voltage, both voltage curves climb up to VDD, right? And once you reach to a reliable point, basically, this is at this point you can say that your cell charge is mostly restored. This is a theoretical one. Okay. In practice, you have the time in here. So even though the analog process completes here, and after this, it's just going to be saturated here. We put the timing parameter here. So we just wait for nothing. So why does DRAM need this extra margin? Because of process variation and temperature dependence. So DRAM cells are not equal. And this leads to extra timing margin for a cell that can store a large amount of charge. And there's also temperature. We'll talk about it in a little bit. So if our cells are the same size, the same charge, the same latency, all of them will show the same behavior, right? But in real, some cells are smaller, some cells are larger, some cells are weaker, some of them are stronger. So we have different size, different charge, different latency. Okay. I guess I already talked about all of these. This is more like a circuit representation of a DRAM cell. So we want to provide this contact basically to connect this capacitor to bit line. And this is your cell capacitance, this is your contact resistance, this is your access transistor. And if you have small cell, it can store small charge, and it has small cell capacitance, high contact resistance, slow access transistor. As a result, you will get high access latency. Okay, I guess that's enough for process variation. I hope it's clear. Do you have questions about process variation? Okay. And in temperature dependence, so DRAM leaks are, sorry, the DRAM chips are leaky by default, right? But they leak charge faster in higher temperatures and leads to extra time and margin for cells that operate at low temperature. Okay, so in room temperature and in hot temperature, when you compare, you have smaller leakage in room temperature, larger leakage in hot temperature. So basically you have smaller charge in room temperature and high temperature and larger charge in the low temperature. So it directly affects how much latency you would have when you activate a row, and how frequently you need to refresh row as well. Okay, so DRAM time parameters are defeated by the worst case. The small cell with the smallest charge in all DRAM products operating at highest temperature, and there's a large timing margin for common case. Our idea is to optimize DRAM timing for the common case. So it gets the current temperature and current DRAM module as input, and it leverages the observation that DRAM cell can store much more charge in the common case, because your current temperature is mostly lower than the worst case temperature, and the cells you're accessing are mostly better than the worst case cell. I think it's quite straightforward at this point. Okay, so when you sense, you can sense at lower latency. When you restore, you can restore at lower latency. When you precharge, you can also precharge at lower latency. And we want to see like how lower we can go. So this is a picture of the setup that I already showed earlier. This is an early version of our infrastructure called SoftMC. And yeah, this is the full paper. And as I said earlier, we have a newer version of this DRAM bander, and you can get access and start testing DRAM chips if you're interested. And these are some pictures of DRAM bander. Okay, let's go back. So we want to understand how this operation happens in real chips. So when we have more charge, stronger charge flow happens and faster sensing happens. And we observe actually in 115 DIMM, the DRAM modules. It's several hundred chips basically. When you measure the real timing, activation timing, you observe 17% reduction without any errors. So you can reduce your activation latency 17%. You don't see any errors. So this is your guard band, right? You're waiting for 17% of the time for no reason. Well, it's not exactly no reason, but I mean, in this operational case, right, nothing happens. Okay. So for other latency parameters, TRAS is the charge restoration, right? So you can reduce it by 37%. And for writes, you can reduce by 54%, and you don't get any errors. So you can optimize DRAM timing parameters online based on the chip you're accessing, the part of chip you're accessing, and the temperature. And you can improve system performance basically based on that. So system monitors DRAM temperature and use appropriate DRAM timing parameters. And you need to have the manufacturer provide some set of characteristics as well, or you can rely on reverse engineering as well. Okay, so this is some statistical data. So in server cluster, you usually have something like 34 degrees Celsius. This is because you have a good air ventilation and cooling infrastructure there. In your desktop machines at home, you usually see 50 degrees around. This is the temperature you see in the DRAM chip, basically. It's not like in the processor. And DRAM standard is optimized for 85 degrees Celsius. Okay. So these statistics, I believe, are coming from these previous works. Okay. In common case, we operate at lower voltage, so lower temperature, so we can use lower latency values. And we can reduce sensing by 17%, like restoration 37, 54, and Precharge for 35%. And yeah, there's some evaluation in this paper. You can go check the details. And they test like some single core workloads. They get an average improvement of like 1.4% for non-intensive workloads and 6.7% speed up for intensive workloads. And then average across all of them, it's like around 5%, right? But this is for single core workloads. In a normal case, you usually have multiple programs running on your machine. So when you go to multi-core workloads, the benefits increase a lot. So you get like 14% for memory-intensive applications and 10% on average. Okay, good. So LDRAM has the advantages of like simple mechanism and it reduces latency. It has significant system performance and energy benefits. Its benefits are higher at lower temperature because you get temperature as an input. And it has low cost and low complexity. The disadvantage is that you need to determine reliable operating latencies for different temperatures and different DRAM modules, and it requires a higher testing cost. And it might not be that difficult for low temperatures. Okay, so this is a full reference, and please go check that. So yeah, so LDRAM explores latency variation across time, different time, and across chips. But the question is there also latency variation within a chip? I guess I already said that there is, so I shouldn't ask you this question, I guess. So there is across different parts of the chip. And yeah, it's already there. So this is TRCD. TRCD is the raw activation latency. You send the activation command, and this is the time you need to wait for a reliable read operation, right? So this, for a set of chips, I believe these are DDR3 chips that we tested at that time. The nominal latency value you see is 13.1 nanosecond. So this is the value specified in the standards. And if you try accessing data in these rows, with 12.5 nanoseconds, for example, you don't see any bit flips. 10.0 nanosecond, you don't see any bit flips. And then As you reduce it to like 7.55, 2.5, you start seeing bit flips. But the key is, so I guess the first takeaway is that there is this large guard band. And on top of that, you also have different characteristics across DIMMs and in different parts of the DIMM as well. So in some DIMMs, you have very few errors. In some DIMMs, you have many errors. Yeah. And modern DRAM chips exhibit significant variation in activation latency. And they're concentrated in certain columns of cells. So I'm not sure if it's visible for you, but some columns here. So it's like x-axis columns, y-axis rows. This is like a heat map, how many bit flips you will see over there. And there's some concentration on these columns and these columns. But on these columns, for example, there's no concentration. Okay. This is just an example from a chip, right? It doesn't have to be exactly the same behavior in all the chips. Okay, yeah. So our observation is DRAM timing errors are concentrated in certain DRAM regions. So can we have some flexible latency used for these DRAM chips based on which part of the DRAM chip we are accessing? So we divide the memory into regions of different latencies, and from the memory controller, we use lower latency for regions without slow cells and higher latency for regions with slow cells. So this is some plot based on DDR3. So the baseline is what is specified in the specification, right? It's like 13 nanoseconds TRCD and 13 nanoseconds TRP. TRCD is again activation latency. TRP is precharge latency. And if you look at like fraction of cells and their latency values in these like 3 different DRAM modules, you see that a vast majority of the cells in this module have like 10 nanoseconds of activation latency. In this module, it's like 7.5 nanoseconds of activation latency. But you also see like some cells here, 7.5 nanosecond, and here 10 nanoseconds, right? So there is some significant variation within the DRAM chips as well, as you'll see here. So this plot published in Sigmatrix in 2016 by Kevin. Okay, so these are the actual fractions. So if you go to this, if you're using this module by any chance, you can just go with 7.5 nanoseconds, and for 99% of your cells, you will not see any bit flips. Okay. Okay, so this is the performance impact of reducing these latencies. So 1.0 is the baseline performance, basically, that uses the latency values specified in the standards. For different DRAM modules, you can get different performance benefits because their characteristics are different. And this is your upper bound. If you reduce the latency for the minimum value that you observed for like all the cells, you would get this kind of performance improvement. So Fly DRAM improves performance by exploiting special latency variation. And it comes with the advantages of reducing latency significantly, exploiting significant within chip latency variation. And the disadvantages, again, you need to test it really rigorously. And this is comparatively to AL DRAM. It requires a little bit complicated controller because now you need to have a data structure over there that tells you like based on what portion of the memory you're accessing, which kind of latency you need to use. You can see the whole paper here. It's published in 2016 Sigmatrix, as I said earlier. It's a nice read. It's not very long. It's just like 12 pages. There is a follow-up of this work that I will talk really briefly this time. In a little bit. It has like 45 pages of analysis, including also the supply voltage. It's called Voltron. It was one of my first, like one of the papers that I contributed in my first year. It has really a special place in my heart. Okay, so this is another follow-up paper, Solar DRAM, that actually puts everything together in terms of this variation in latency. Actually, this is just a screenshot from Jeremy's YouTube channel. Jeremy is the first author. He works for Apple nowadays. So here you can see actually, so this is like DRAM columns and DRAM rows, and you can see some columns being more vulnerable to low latency accesses, right? So it's like a very clear pattern here. So this is really nice about this paper. It looks at all these like features of the spatial variation. So please go watch this video. It's a nice talk in ICCD 2018. And I guess you can try contacting him, or if you have questions, you can ask us as well. So why is there spatial latency variation within a chip? So this is the next question we have, right? So why do we have some chips faster, some chips slower? Okay. Yeah, my Siri just wanted to talk a little bit. I guess I talk too much. You have some cells slow, some cells fast, right? And up to now, we were just talking about manufacturing process variation. So here, this is another paper published in 2017, Sigmatrix, if I remember, that investigates if there is any variation imposed by the design decisions. So here, if we look at a sense amplifier, as your cell, sorry, not sense, this is a subarray, a cartoonish picture. If your cell is farther than sense amplifier compared to other cells, it has a larger latency. If it's farther to the word line drivers, again, it has a larger latency. So as you go to this region, you're faster. As you go to this region, you're slower. So there's a systematic variation in cell access times caused by the physical organization of DRAM as well. And this is called design-induced variation-aware variation. And this paper proposes the design-induced variation-aware mechanisms here. It provides some online profiling methodology first. It identifies the slow regions, and it provides a dynamic low-cost latency optimization. So it takes into account the process variation based on the random errors. You know, some cells are weaker just because of process variation, and some cells are weaker because of the design decisions. So you need to decouple them, analyze them separately. So this paper does exactly that. So for random errors, it employs some error correcting codes so that in theory, these manufacturing process induced weak cells are uniformly distributed. So error correcting codes are good at actually covering their reliability weaknesses. And for design induced variation, it uses some online profiling tool, gets the locations of the weak cells and treats them accordingly. So, okay. So by doing this, it reliably reduces the DRAM latency. And the latency reduction is great at 55 degrees Celsius. It has like 31% reduction in read latency, 25 in 85 degrees. So this is for ALDRAM's result, right? So this is the first paper that I mentioned in this part. And Diva improves this 31 to 35, 25 to 34. Because it also accounts for design industry variations. And on top of that, it also enables some shuffling algorithm in place in the data, and it further improves the benefits. And you see some significant benefits for write latency as well. Yeah, Diva DRAM reduces latency more aggressively than ALDRAM, and it uses ECC to correct random errors. And it automatically finds the lowest reliable operating latency at system runtime, And also it reduces latency more than prior methods with ECC. And it also supports higher temperatures. Sorry, it still supports high latency reductions at high temperatures. Yeah, the disadvantage is that it requires knowledge of inherently slow regions, and it can be hard to recover, actually. It might require even more expensive testing, and it requires error correcting codes as well. And it imposes overhead during runtime profiling. And it's a bit more complicated in the memory controller because it needs to support this shuffling, error correction, everything together. This is a full reference for that, and please go check the paper. I'm not sure if we have the video for this. Okay. There's another aspect of this, right? Application data. So it's 3:16 now. Let's take a like 4-minute break until like 3:20. And then I'll talk about some applications that can benefit from these latency variations. Does that sound good? Thank you. Okay. Sorry. I think this is becoming too dense, and 4 minutes is not enough. But I have to cover some stuff, so I'm sorry. We need to start. Okay, so we looked at so far how latency varies across different parts of the chip, with temperature, with across DRAM chips, and yeah, why one size fits all approach doesn't work for every case. And now we will look at how applications are affected. How can we use this latency variation to improve our applications? So the first one is data-aware DRAM latency for DNN inference. So I guess DNN is like a widely known term now, deep neural network. It's the evaluation of deep neural network is quite DRAM intensive process, and especially for large networks that do not fit into your cache. And some data layers in DNN are very tolerant to errors. You can have a few bit flips in your weights, and it doesn't actually hurt your accuracy too much. And the idea here is to reduce the DRAM latency and voltage so that in those layers, even if we have some bit flips, it's okay. And we can improve performance by doing that, right? So by doing this, we can achieve a user-specified DNN accuracy target by making training DRAM error aware. And this is basically a data-aware management of DRAM latency and voltage for deep neural network inference. So there's a good plot here, actually, but I don't want to go through every single point here. So basically, so you have some input feature map. I think it's called that. And weights here, so different IFMs and weights, and you see the maximum tolerable bit error rates for those. So up to like 2% bit flips here, for example, for this particular one, it's okay. You know, the accuracy tolerates it, so you don't lose much, basically. So based on this data, what this paper does is it classifies different IFMs and weights into different categories and maps the more error-tolerant DNN layers to the DRAM partitions with lower voltage and latency. And it defines 4 DRAM partitions with different error rates, less than 2%, less than 5%, 6%, and 8%. And the key idea is to enable accurate, efficient DNN inference using approximate DRAM. And it's an iterative process that has 3 key steps. It has a boost in DNN error tolerance step, DNN error tolerance characterization, and DNN to DRAM mapping. And basically, it keeps iterating here. So it gets the error tolerance data. It maps the DNN according to DRAM regions, and then gets an accuracy, and then does this loop several times, and then converts to a good accuracy and energy efficient point. So it reduces the DRAM energy reduction. Sorry, not reduction. It reduces the DRAM energy consumption significantly, more than 10-20% here, more than 20% here, yeah. Yeah, on average, it's 21% DRAM energy reduction, maintaining accuracy within 1% of the original target. Okay, so it also provides some speed up, on average 8%, and for some workloads, it achieves 17% speed up. And even achieves close to ideal speed up, possible via TRCD scaling. So TRCD is the raw activation latency that I kept talking about. So compared to GPU, Iris was an accelerator, and the tensor processing units as well. It provides a significant energy reduction for these platforms, basically. And this is the full paper. You can take a look at that. And there's a short 90-second lightning talk video as well. This was published in Micro in 2019. Okay, and there's a full lecture about that for like 38 minutes long. Luis Orosa, who is the head of Galicia Supercomputing Center now, was here with us, and he gave this lecture. So you can, yeah, just like watch this lecture. It's quite good. Okay. So basically, what we try to do here is exploiting the memory error tolerance with hybrid memory systems. So you have different applications and different data structures with different tolerance points, and you also have like different memory components with different error vulnerability. So you basically match them, right? So you put vulnerable data here, tolerant data there. Yeah, so vulnerable data to reliable memory, tolerant data to the, yeah, not unreliable, but you know, more low latency. So it gives you some heterogeneous reliability memory. And this is an idea actually explored in DSN in 2014 and later on leveraged by this IEDM work. Okay. So you can have some ECC protection in this reliable memory to, you know, protect vulnerable data. You can have more well-tested chips here. Here you can be more relaxed, basically. You can reduce the testing cost. You can avoid, you know, get away without ECC or parity. So basically, this is the idea. Okay, so on Microsoft Web Search workload, it reduces the server hardware cost by 4.7% and achieves single server availability targets of 99.90%. So this is a quite good work of that time. So this is not particularly related to Eden, but you know, the same idea in high level. And different applications, of course. So for doing such works, as a step one, you need to characterize and classify the application memory, error tolerance, and you need to map the application to the relevant memory space, basically. You have reliable and low-cost parts. So you need to basically, you know, map it in a way that, you know, you will get high reliability and high performance, low energy consumption at the same time. Okay, so this was the application part. I will talk about supply voltage levels as well. So this is a paper that I referred to from FlyDRAM. So this paper was published in 2017. If you get the full paper, it's quite large. It's like around like 40, 45 page long. But there are like shorter versions of that as well, like 12 page, even like 2-page extended abstract. You can take a look at them, and I think we had a larger lecture of that as well. So the problem here this paper tackles is the energy consumption of DRAM. And some earlier works show that energy consumption of DRAM can take more than 40% of the system energy consumption. So it's important to reduce DRAM energy consumption. And how does reducing voltage affect the reliability? Because when you reduce voltage, you can save energy. And how does reducing voltage affect DRAM latency? So we want to answer these questions in this work. And how do we design a new DRAM energy reduction mechanism? So this is your DRAM voltage. You provide the supply voltage. Sorry, this is your DRAM module. You provide the supply voltage, and you can adjust supply voltage for every chip on the same module separately. We use SoftMC again to do the DRAM characterization. And this is again DRAM Bender, the newer version of SoftMC. You can use it. You can do this kind of analysis as well. So we test in this paper 124 DDR3 chips, and we iteratively read every bit in this chip for different voltage levels. And we reduce voltage from 1.35 volts down to 1.0 volts. So the reason we stop here is that when we go to like 0.9 or something, the chip doesn't work at all. So this is a plot that gives the key takeaway of this paper actually. So on the x-axis, we have the supply voltage. On the y-axis, we have fraction of the cache lines with errors. And we start from 1.35 volt, which is the nominal voltage for DDR3. And as we reduce the voltage, depending on which vendor the chip from, you have different curves here. So you have some minimum voltage levels that we call Vmin that give you no errors, basically. They're like the fraction of erroneous cache lines is 0 at those points, basically. So for vendor C, if I remember it was Hynix, you can reduce down to 1.3. A and B, Micron and Samsung, you can reduce down to like 1.15. And by reducing voltage below Vmin, you can have some increasing number of errors. If you want to stay in the reliable margin, you shouldn't reduce it below that point. So we have some circuit model that we looked at the voltage scaling and latency trade-off here. And we realized that it's actually just like the circuit model, right? It's not like some surprising finding anyway. But when we reduce voltage, if the latency increases. So in contrast to the previous work, if we reduce voltage in this work, and if we increase the latency above the nominal latency, then we can still provide the reliable operation, right? So the key idea is to have that basically. You want to have the low voltage operation, but now you might operate with higher latency. Okay, so it measures the minimum latency that does not cause errors in DRAM modules. And this is a bubble plot where the bubble size shows the population, and you also see like the fraction of the population for each bubble, for each X value. So you reduce supply voltage. Here you have 100% of the modules working reliably at the activation latency of 10 nanoseconds. So nominal was around 13 nanoseconds, right? So you can reduce it to 10 for 100% of the modules here. Once you come to this point, for example, you can have 14% of the modules, sorry, 40% of the modules that work at 12.5 nanoseconds, right? And then here, like 10% of the modules require like 14.5 or 15 nanoseconds here. Yeah, so this is distribution of the latency in the total population of the modules. Modules, yeah. And in some of them, you don't see like they add up to 1.0. This is like add up to 0.9. It's because like 10% of them don't work at this point. Okay, so this is the lower bound of the latency because, we don't know exact latency values. This is a limitation of the infrastructure. We say that, okay, 10 nanoseconds work, 7.5 nanoseconds do not work. And the actual latency is somewhere in between. Okay, so the takeaway is DRAM requires longer latency to access data without errors at lower voltage levels. And when we look at the distribution of these voltage levels, this is an example from one chip where we observe that the errors actually are concentrated in particular banks. This is not true for all chips, but quite some significant fraction of the chips, we have this kind of distribution. By the way, for all tested DRAM chips, we have these plots, these heat maps already in the GitHub repo. So you can go check that as well. So we observe that errors concentrate in certain regions. And based on that, we propose a mechanism here called Voltron. Voltron takes the input from user as a performance loss target and selects the minimum DRAM voltage without violating the target. And the problem is that how can we predict the performance loss due to increased latency under low DRAM voltage? So we have the performance loss target. We don't know what kind of latency is okay. So we need to predict that. For that, we use a linear regression model where we get the applications characteristics, memory intensity and stuff, and also the DRAM voltage level. And then based on that, it predicts a performance loss. And based on that, it provides a minimum voltage level. So we use this minimum voltage level and the latency value that corresponds to this voltage level, and then get the application running at that point. Compared to prior work, which is memory dynamic voltage frequency scaling, Voltron provides better savings basically in terms of energy. And it always missed the performance targets. So we say like 5% performance target loss is okay, and it achieves actually this energy reduction at like even better performance than this target. Okay. Advantages: it can trade off between voltage and latency to improve energy and performance, and it can exploit the high voltage margin present in DRAM, and it requires finding the reliable operating voltage for each chip and also the latency values for those, right? And there's again some complicated stuff in the memory controller. Okay, I gave this lecture in the past in 2019. There's a longer lecture of this talk, this paper, so you can go check the details over there as well. Okay, this is another field that I will go through quickly, hopefully. So we can reduce these memory latencies, and instead of operating the DRAM chip in a reliable point, we can operate it at the point where like we want some reliability, some unreliability. And we can support some generation of some security primitives. So for security applications, true random number generation is important. And also evaluating physically unclonable functions are some key operations, primitives for basically like authentication kind of tasks. And you also sometimes want to quickly destroy the data inside DRAM chip so that it's not compromised, right? So to do this, we can leverage these observations that we have with the DRAM latency parameters. Okay, the first word is DRAM latency, PUF. PUF stands for physically unclonable functions. This is the talk that Jeremy gave, I believe, in 2019. And this is the full reference. And okay, there's no detail about this, but I'd like to mention that it was also picked for IEEE micro top picks and awarded with honorable mention. And sorry, this is D-range. Okay, for DRAM latency PUF, basically what you do is like you want to identify if the chip you're using is the chip that you think you're using. And by violating latency parameters, you get a distribution of bit errors, and it gives you a key that is not clonable by any other device, right? So it is a security primitive. Okay, let's move to D-range now. This is the random number generation work. It generates true random numbers, leveraging the true random processes in the DRAM chip that is caused by the manufacturing process variation, right? And yeah, this one is picked for IEEE top picks and awards with honorable mention. Okay, this is Jeremy's work as well. The motivation is that high throughput true random numbers enable system security and various randomized algorithms. And today, many systems already have DRAM, but they do not have true random number generator dedicated hardware. And the current DRAM-based TRNGs either do not sample a fundamental non-deterministic entropy source, or they are too slow for continuous to high throughput operation. So the goal is to address these issues basically. And the proposal is D-range, reduce DRAM access latency below reliable values. So you know that you will get bit flips, and exploit DRAM cells failure probabilities to generate random values. Okay. They test 282 real LPDDR4 DRAM chips this time. And then they show that they can generate true random numbers at this band throughput. And this is significantly higher than the state-of-the-art 200x. And latency is also significantly lower, 180x, right? Okay, so these latency failures come from accessing DRAM with reduced timing parameters. And this is determined by a random process variation, and some cells fail randomly. So, okay, so you do the activation, and this is how the bitline voltage changes, right? And you read at this point. When you reduce TRCD, You can have bit flips around these regions, for example, and this curve changes from cell to cell based on the process variation. And if you reduce this latency to this point, for example, these cells will observe bit flips, these cells will not observe bit flips. Okay, and this is because you have this random process variation. And there's high chance to fail for these like weak cells and low chance to fail for the strong cells. And there are a set of cells that fail randomly. So the fail or bit flip probability of a cell is close to 50%. It doesn't always fail or it doesn't always not fail. So these cells are random number generation cells, and they generate random values by repeatedly accessing these RNG cells, and they run their the data they collect through some statistical test that measures randomness, and then it passes with a throughput of 717 megabit per second, and with this latency value, and with this much power consumption per bit. So this has been the state of the art for some time, and I just beaten by some other of our papers that I will talk about next. So, but you can go and check this videos and the paper. It's quite interesting to see that you can introduce some unreliability in your system, and you can actually generate some security primitive. This is a follow-up work that beats DRANG. This is QuaTRNG. The idea is quite similar, but yet quite significantly different at the same time. So in high level, again, we want to perform some unreliable operation and generate random numbers, but the operation we perform here is quite different. So this paper is motivated by the need for true random number generation. It's critical for many applications, for security, for simulations. I guess you can include Bitcoin mining here as well. And this can only be obtained by sampling random physical processes, and not all computer systems are equipped with TRNG hardware. And yeah, so DRAM-based TRNGs are low cost and high throughput. It refers to DRANG here, and it requires no specialized hardware, and it's an open application space. And also, there's another thing here, actually, another motivation. Processing memory systems also need random number generation, and they definitely don't have the necessary equipment to generate random numbers, right? And DRAM-based TRNGs can be a good candidate for those. Okay, so before DRAM-based TRNGs, the previous ones were fundamentally slow, or they were effective. They were not able to effectively harness entropy from DRAM rows, and our goal is to develop a high throughput and low latency TRNG that can be implemented using commodity DRAM devices. And the key observation is that if you carefully engineer some DRAM commands, you can, this is a malfunction of the DRAM chip, basically. You violate some timing constraints, you end up activating 4 DRAM rows in real chips simultaneously. So you activate these 4 rows, and you put basically high voltage to 2 of the cells and low voltage to 2 of the cells. And when you just like get the average voltage, it's closer to VDD over 2, right? And then you will get random data based on that. This is the key idea. So this is the command sequence you perform, and you violate some timings, and you get random values. And what they do is they understand that some bits randomly fail when you do that, and then they measure the Shannon entropy, and then as a second step in this paper, these random bits are fed into a hash function to further improve the entropy, basically, and it gives you a true random number at the end. Okay. So yeah, so they test 136 real DRAM chips using DRAM Bender, Again, DRAM vendor. And the key results is that they get this 5.4 gigabit per second TRNG throughput per channel. It outperforms the best, which was D-range at the time. And it comes with very low latency. It passes all 15 NIST randomness tests, and it incurs negligible area cost to contemporary CPU and negligible memory overhead because you need to dedicate some rows for random number generation. You lose that capacity, but it is around like 0.002% for this kind of throughput. If you increase the memory overhead, you can increase the throughput as well. And entropy changes with temperature. It remains stable for at least up to a month. Okay. So this is the conclusion. We get some good throughput, low latency, good random numbers, and this is the paper. Okay. So there's a longer talk as well. I think Ataberk didn't present this semester. Maybe in the cutting edge, one of the cutting edge lectures, he will present it. I am not sure. But this is it about true random number generation. I have 13 minutes and not many slides. I think I can cover all of these. So we have more papers working on the latency reduction. So this paper looks at if we can reduce the refresh latency and make things work reliably still. It's a good read. It's a short paper. Please go read that. And yeah, this paper is quite interesting as well. The key idea, okay, we will go through this paper. Okay, our goal is to reduce average DRAM access latency with no modification to existing chips. And our observations are a highly charged DRAM row can be accessed with a low latency because you highly charged row and there's not much time passed. You still have very high charge over there. When you activate, the charge sharing process will happen quicker. You will have a larger delta in the bit line voltage, and then you can sense it and amplify it in a faster way. This is the key observation. And a row's charge is restored when the row is accessed. So whenever you activate the row, you restore the charge. And a recent access row is likely to be accessed again because there's something called row level temporal locality. This is a behavior that many workloads exhibit. They access a row, and after a while, they access the same row again. So that row has high charge basically at that point. So the mechanism is charge cache. It provides low cost and it comes with low cost and no modifications to the DRAM chip, and it provides high performance around 10% on average for 8-core workloads, and it reduces the DRAM energy consumption by 8% on average. Hassan, a recent graduate from our group, was the lead of this paper, and he gave a long lecture in 2018, so you can take a look at that as well. So this paper was published in Micro in 2018. It's also one of the top conferences. Okay, so this is another paper that is slightly older, from 2014, from Kevin Chang again, that proposes to parallelize refreshes and accesses across different subarrays. And I hope that idea sounds familiar to you, because last week I covered this paper, Hidden Row Activation, where we do the same thing on the real DRAM chips. So this was published in 2014, and this is in 2022. After 8 years, manufacturers didn't provide official support, but we ended up finding that they actually have this functionality in DRAM chips. Okay, so we also do works about looking at the power consumption. So this is a nice paper. What your DRAM power models are not telling you. They are just telling you the worst case, or in some cases even the common case, not even the worst case. Sorry, not common case. For some energy consumptions, they provide you a case that is defined in the specification, but it is not a representative case of the common case, or it is not the worst case. It is basically giving you a rough idea of the energy consumption of DRAM chip, but it's not giving you some accurate information. And to get that accuracy, basically, we added this particular thing in our infrastructure where we did this is a coil, basically. All the current that is going to the DRAM chip goes through this. And then we measure the current consumption of this. And then we repeat all the tests that are in the specification and show the differences of the real values from the values in the specification in this paper. So it's there's it's a good paper, a bit long but interesting. And we for this one as well we use earlier version of DRAM bander. Okay, in summary, fundamental low latency computing architecture is important, and this is a challenge and an opportunity for future systems. At the same time, it comes with reasons and challenges of these that we kept talking about today, and it seems like the current research, all the papers that I talked about today, tells us that we can reduce memory latency with a change of the mindset. We can push the boundaries a little bit. We can end up having better latency, better energy consumption, higher performance. We can address these issues with a slight change in the mindset. And the other takeaway is that main memory needs intelligent controllers to reduce latency. If you remember, in some papers in the cons part, there was a mention of more complicated memory controller. It means there is some more intelligence needed in the memory controller. And we need to follow some solution principles. So data-centric design, I think obvious because of PIM, right? We need intelligence in pretty much all components, and we need a better cross-layer communication, better interfaces. And we also need to have a good understanding of better than the worst case design so that we can have an understanding of the common case. We need to account for heterogeneity, and we need to design computers and the mechanisms we implement in computers in a flexible and adaptable way. And this comes with like some open-minded approaches, right? And then we have a lot of things to leverage for a given system. Okay. And the ideas we talked about today are also applicable to other domains, for example, SSDs. And I guess you will hear about SSDs in the following weeks quite a lot, so I'm not going to get into that. So this is our 4 key current directions. We care about security, reliability, safety, energy efficiency. For this, we invest a lot on memory-centric architectures. Today, we talked about low latency and predictability. I guess you have a rough understanding of at least what's going on in Subarray, how we approach this problem, and how we leverage how we push the boundaries for reducing the latency. And you will hear more about AI ML applications, genomics acceleration, and their impacts on medicine and health starting from tomorrow. And this is the end of my lecture, and we are 6 minutes early. So I guess I just rushed a lot towards the end. I didn't stop enough, maybe. I didn't get enough questions. So please ask questions if you have any. Or people in YouTube. Yeah. Yes. Okay, this is a really good question. I think you should ask this question to Ataberk as well at some point. I can say that maybe I should repeat the question as well, right? So in QuaTRNG, we generate some bits randomly, and then we input them to a hash function, and then it gives us the random number generation. Does the hash function add any additional security to that? In my opinion, it doesn't fundamentally do that. But it allows you to, mix the TRNG with pseudo random number generation a little bit. and improves your throughput, in my understanding. Ataberk might be, might have some opposite idea, and maybe he would say the opposite. And I guess you should challenge him if he will give the lecture. Do we have that in the plan? QuaTRNG? Okay. By the way, the first author of QuaTRNG will be lecturing next week, right? Memory controllers. So you can ask him this question directly. Other questions? Then I guess we can finish up early today so that we don't also disrupt the other lecture that is going to happen in this classroom. Thank you all for joining.